Hello, welcome to you all in my channel Mechanical Engineering Concept. In this lecture, I am going to solve question number 10.2 taken from Machine Design book written by V B Bhandari, and the chapter is related to the design of the spring, and this topic is related to the helical spring. The question is asked that in an automotive plate clutch, 6 helical compression spring arranged in parallel provide the axial thrust of load 1500 Newton. The springs are compressed with 10 mm to the provide this thrust force. The springs are identical and spring index are given to us is 6. The springs are made up of cold drawn steel wire with ultimate strength of 1200 Newton per mm square. The permissible shear stress of the spring wire is 50% of the ultimate strength, and modulus of rigidity given to us is 81370 Newton per mm square. The spring have square and ground ends. There should be a gap of 1 mm between adjacent coil. When springs are subjected to the maximum force, design the spring and calculate wire diameter, mean coil diameter, number of active coils, total number of coils, solid length, free length, required spring rate and actual spring rate. So the spring will something look like this. If I suppose to understand what the dimension or what are the unknown values I need to calculate, suppose this is the spring, so I need to calculate this wire diameter by which wire I can design my helical spring, mean coil diameter, which is the distance between center of the two ends. Okay. Free length will be length of spring without load. Solid length will be length of spring after removing or neglecting this gap between adjacent coil. Active number of coils, it means the coil which participate in deflection, and total number of coil which is included with the number of coil which are not deflecting plus active number of coils. Okay, this is the mean diameter, mean coil diameter, this is the outer diameter, this is inner diameter. Okay, so given data in this problem is load W is 1500 Newton, spring index 6, okay, gap between adjacent coil 1 mm, G is equal to 81370 Newton per mm square, SUT ultimate tensile strength is given to us 1200 Newton per mm square. Okay, one relation given to us is permissible shear stress is the 50% of SUT. It means 0.5 times of SUT will be the 50% of SUT. It means 1200 into 0.5 will become out as 600 Newton per mm square. And one more data is given to us is here we have a 6 number of spring which are 6 helical compression spring are arranged in order to provide the comfort or support to the other element. Okay, so let me calculate first unknown data, which is small d, wire diameter. How can I calculate this? We need to remember this formula, shear stress 8WD by pi d cube into kW. As we know, spring index C is capital D by small d. Capital D and small d are unknown, but C is given to us is 6. Then I can write this formula as, this is in suffix in lowercase, okay, 8WC by pi d square into kW. W is the thrust load, C is the spring index, small d is the wire diameter, Kw is the wall correction factor. W is given to us, C is known to us, small d I wanted to calculate, tau I already calculated, and Kw is the wall correction factor, which is 4C minus 1 divided by 4C minus 4 plus 0.615 divided by C. Okay, and this formula I can take from equation number 10.4 from design data book written by V B Bhandari. This one, and page number 10.11 will be the page number from machine design data book. Okay, C is known to us, then Kw will be come out as 4C into 6 minus 1 divided by 4 into 6 minus 4 plus 0.615 divided by C. Then Kw will be come out as C. In place of C I need to put 6. 4 into 6 minus 1 divided by 4 into 6 minus 4. 4 into 6 minus 1 divided by 4 into 6 minus 4 plus 0.615 divided by 6. Kw will be 1.2525. 1.2525 will be the value of wall correction factor. Always remember, here we need to select wall correction factor. It means wall correction factor shows the curvature effect in the spring. If we consider without wall correction factor shear stress, then we need to consider this formula, this one. One second. Yes, this one, which is given to us in this equation number 10.19. This is the correction factor for direct shear stress, which is not considering the wall correction, which is not considering the curvature effect, which is given to us in this page number 10.13 in design data book. Okay, 1 plus 0.5 times of C. This is the direct shear stress correction factor, not of curvature effect, without curvature effect. Okay, so you need to remember this formula mainly. This is the without curvature effect. This is not that much important, but for basic information you can remember this one also. Okay. So Kw is known to us. Now tau, in this formula I need to put the unknown values, known values. Tau is 600 is equal to 8. W is given to us here is 1500 Newton. C is 6 divided by pi into d square, and 1.2525 will be the value. Now solve this. Transfer this d square to here and 600 to here. Okay, for calculation point of view. 8 into 1500 into 6 into 1.2525 divided by pi into 600. D square will come out as 47.84, and the square root of that is 6.91. D square will come out as 47.84. Okay, mm square, and D will come out as 6.91 mm, which can be written as D is approximately equal to 7 mm for calculation point of view, simplifying the calculation. So first unknown we calculated. Second unknown I wanted to calculate capital D. For that we have already know the value of spring index 6. Spring index capital D by small d is equal to 6. Small d we already calculated. 6 into 7 will be the 42 mm mean coil diameter. Next unknown I wanted to calculate is the mean total number of active coils. Active coils I can represent with the symbol of capital NA. For that I need to remember this formula. Delta is equal to 8W d to power 3 into Na g d to power 4. This formula can also be remembered something like this, because capital D by small d is known as spring index. So this formula can look like something this. Here we know the value of delta, which is given to us is equal to 10 mm. W is 1500, C is 6, D small d we already calculated as a 7 mm, and G is 81370. So 10 mm is equal to 8 into 1500 into 6 cube into Na, which is unknown, 81370 into 7. Put this value, all this value into the calculator. 10 into 81370 into 7 divided by 8 into 1500 into 6 cube. Na will be 1 mistake I have done, sorry, one mistake I have already done. I think this value is wrong here. One given data I have neglected, which is this one, total number of coil, total number of spring. Here we have a total number of spring 6, which can be something understand like this. Suppose this is the plate. In this 6 spring are arranged in parallel order. This, and W is applied, which is 1500. This will distribute equally in this spring because this spring have a parallel arrangement. So for one spring the load will be 1500 divided by 6. Okay, which is equal to 250 Newton. So I need to put here in place of 1500 250. I need to put here 250 Newton. Then my value will be something different. Okay, one correction is there. So 8 into 250 into 6 into 1.2525 divided by 600 into pi. Take a square root of that. 2.82 will be the value. This is wrong. 2.82 mm will be the value, and in place of 7 I can round it off this value as a 3 mm. So capital D will also be changed. 6 into 3, this will be come out as 18 mm. Okay, you need to remember this. If suppose number of springs are given to us and they are parallel in arrangement, then applied load will distribute in each spring by dividing that load into divided by number of spring, by which I can understand that each one spring have a load of total number of divided by number of spring. Total load divided by number of spring. Okay, capital D will be that much, and in place of 1500 here also I need to put 250. So the value will be, the new value or for the corrected value of Na will be 10 into 81370 into small d is 3, okay, 3 divided by 8 into 250 into 6 cube. This is spring index. The value will be 5.65. and it will be 5.65 coils. So I can't design, or we cannot design with number of coils having 5.65 value. We cannot design a spring with a fraction value. We can design a spring with a length of number of coil 2.5, 3, 6, 4, 7, 4.4, 4.5, 7.5, 10. Okay, not a fraction value. So I need to standardize this value as a 6 coils. Okay, this is the total active number of coils which participating into the deflection. Okay, number of active coils are coils which are due to load application will deflect. Number of passive coils which are not participating in the deflection due to application of load. Next, fourth value I need to calculate total number of coils. To calculate this, I need one condition which is given to us in this problem, is that the spring having square and ground ends. So spring is used to square and ground ends. So to calculate and to know the formula for that square and ground end, this table number 10.9 which is given to us in table number page number 10.9, this table is useful for us, in which last fourth condition is given to us square and grounded end, in which n represents the active number of coil and t is total number of coil. The active number of coils is equal to total number of coil minus 2. So for square and ground end, for square and ground end, from page 10.9 and table 10.9, active number of coil is equal to total number of coil minus 2. Then total number of coil will be come out as 8 coils. 6 plus 2 will be 8. Okay, this is the new value. Next value I need to calculate is solid length, free length. Okay, so to calculate solid length, as I know, total number of coil into wire diameter will be come out as solid length. Solid length will be something look like this. After the load application, the gap between adjacent coil will be removed completely. No gap further be there in between adjacent coil. This will be known as the solid length. So this is known as the small d wire diameter, and 1, 2, 3, 4, these are the number of turns. Total number of turns into d will be come out as solid length. Solid length, for that small d will be 3, total number of coil is 8, 24 mm will be the solid length. Okay, next free length. So for free length, this formula needs to remember, you have to solid length plus total gap plus delta maximum. Solid length we know 24 mm, we already calculated. Total gap is the total number of coil minus 1 into gap between adjacent coil, which is given to us is 1. It means gap between two coil in this problem is given to us is 1 mm. Gap between these two coil is 1 mm. From here to here, this distance is 1 mm given to us in this problem. Okay, total gap will be total number of coil minus 1 into gap between any two adjacent coil, and delta maximum can be calculated by 8W d to power 3 Na divided by Gt to power 4. Why I need to delta max use? Why I need to calculate this delta maximum? We already have a given to us a known value in this problem 10 mm. Why I need to again calculate this? Because I already rounded off or corrected this Ni value, which has come out as a 5.65 number of coils, which I corrected as a 6. So if I put this value here 6, then delta maximum will be changed. If I increase the value of number of coils from 0.565 to 6, then deflection can also be increased by some amount. So due to that, I need to assign the value of delta. Okay, here delta W is known to us as 250, capital D is 18 cube, Na is 6 divided by 81370, and small d is known to us as 3 to power 4. 8 into 250 into 18 cube into 6 divided by 81370 into 3 to power of 4. The value will be 10.61. If we put 10 here, then the free length will be changed, because Na is not a 5.65. Na is rounded. Na I have taken value as a standard value of 6 mm. Okay, so put 24 plus and 20 in place of NT. I need to put 8 minus 1 into 1 plus 10.61. So the value will be 24 plus 7 plus answer 41.61. 41.61 mm will be the free length. Okay. Now K required and K actual, I need to calculate stiffness required for the spring and stiffness actual for spring. I need to calculate. So to calculate required value, we need to remember this formula, W by del, and for actual value we need to remember Gd to power 4 divided by 8d cube and A formula. How this K actual is different from K required? This K required shows what is actual value I need to required for that 250 kilonewton load. Okay, and this K actual shows actually we have a stiffness value of so much Newton per mm. Okay, so how this formula comes? That in place of delta I can put 8W d to power 3 Na divided by Gt to power 4. So WW will be cancelled and Gt to power 4 will be come into the numerator, and 8 d to power 4 Na d to power 3 Na will be in denominator. By this you can solve. So for that, W is here for our spring is 250, delta is already known to us is 10, actual spring deflection is possible is 10 mm na? So due to that I am considering a 10, not a 10.61. So the value will be 25 Newton per mm actual required stiffness value. Okay, minimum that much stiffness I required for this much amount of load application. Okay, for 250 Newton load I need this helical spring needs to have a spring stiffness of 25 Newton per m square. But actually what is the value of spring stiffness we have? So for that I need to use this formula 81370, which is having g to the power 4 8d cube and a d small d cube we know value of 3 mm 8 18 cube into 6 81370 into 3 to power of 4 8 into 18 to power of 3 into 6 23.54 23.54 Newton per mm. That much spring stiffness we have in the spring, but that much spring stiffness we required for the 6 number of coils which is supporting the load of 1500 Newton, in which one spring supported to 15 Newton. Okay, so this is the way you can solve this problem. You need to remember basic formulas related to this topic for any competitive exam or university exam. If you have a university examination preparation, then you can use design data book written by V B Bhandari if your university allowed. And if you have any doubt related to this topic, then please comment and don't forget to subscribe my channel. Thank you. Have a good day.